Hi, Astronomy. Mr. Janowski here. This is part 4 of the chapters 14 to 15 slides. So, in the first part, we talked about the whole life of a low mass star. In the second part, we talked about the whole life of a high mass star. And then in the last part, we started to go into more detail into the little stages of the lives of stars. So, we're going to continue with that idea and learn about the next couple of stages in this part here. So, what stage of stellar evolution comes after interstellar gas cloud? Remember, that's really the beginning. An interstellar gas cloud is often referred to as a stellar nursery. So that's really the very beginning of this. And what comes after that? It's a protostar. So it's starting to get dense and hot, but it's not actually doing fusion yet. So technically, it's not a star. And what stage comes after protostar? Well, then it becomes a main sequence star, and that's where the star will live for most of its life. And what is the lower limit of the mass range for a star? The lower limit is about 1/10 the mass of the sun. If it's less massive than that, then it won't really ever get going as a star, and such failed stars are called brown dwarfs. And what's the higher limit of the mass range for a star? Well, the higher limit is about 30 times the mass of the sun. So if it were much more massive than that, it would basically shine itself apart very quickly. Now, there are some stars that are much more massive than that, but those stars are very, very rare. So the vast majority of stars are somewhere between 1/10 the mass of the sun and 30 times the mass of the sun. And higher than that, very rare. So here's an idea we saw before. I think this was in chapter 12 when we started learning about the sun, is that stars like the sun and other stars, in their regular life, they're in what's called hydrostatic equilibrium between gravity and pressure from nuclear fusion. So gravity, the force that pulls on all the mass in the universe, well, in a star, you have a bunch of mass together. So gravity is trying to crush the star down, and pressure from nuclear fusion going on in the core is pushing outwards. So that's trying to blow the star apart. And when the star is just cruising along, doing its thing, those two things are in equilibrium. So if we start thinking about the high mass stars, so these have more mass, that's what makes them high mass stars. And more mass means that gravity is going to work more strongly. So gravity is going to crush the cores of these high mass stars down kind of tighter, and that makes them hotter and more luminous. And it needs to work this way because that they need more pressure to support against the gravity that's trying to crush this more massive star. So we also learned the proton-proton chain, in some detail back in chapter 12. So if you're a low mass star like the sun, this is how you basically you start with 4 hydrogen nuclei, you do a bunch of steps, and then you end up with a helium-4 nuclei. So that's how stars like the sun do it. Higher mass stars are hot enough that they can do it a different way. Now, they're also going to do the proton-proton chain, but they have enough energy that they can do it this way. And we're not going to go into all the detail of this because there's a ton of detail. But this is called the CNO cycle. So carbon, nitrogen, and oxygen. And basically those carbon nuclei, nitrogen nuclei, and oxygen nuclei act kind of like catalysts. That it gives the star another way to take hydrogens and smack them into things and go through all these different stages. And ultimately you end up with a helium nuclei. So just another way of turning hydrogen into helium that only the more massive stars with the hotter cores can do. So the CNO cycle leads to convection in the cores of high mass stars. So look at the picture of the yellow one here. So this is like the sun. And remember the layers of the sun. You have the core in the middle. Then you have the radiative zone going out. And then above that, you have the convection zone. So things here are getting hot, which makes them less dense. So they rise to the surface, and then they cool off, and then they come back down. And they kind of cycle around. So material moves around like this. And then above that, you have the 4th layer, the surface of the sun, which I'm sure you all remember is called the photosphere. The photosphere is the surface of the sun. So anyhow, back to a very high mass star. So yeah, in the sun, you have convection out here in the 3rd layer. In a very high mass star, you actually have convection going on in the core. So the hydrogen that's there in the core is getting cycled around, and it's moving all throughout the core. However, you will notice that there is no convection carrying fuel to the core. So that means even though we have all of this mass here in the star, basically everything outside of the core is useless for the star in terms of having fuel that it can use for nuclear fusion. So all of this stuff is out in the radiative zone, and none of it's getting down to the core. So that means they're going to have way less, even though they have much more mass. Not only are they going to go through it faster because they're just going through it faster, but even though they have more mass in total, a large part of that mass isn't actually useful to the star because none of it can get down to the core and be fused. So it's only the very low mass stars, so between 0.1 and 0.4 times the mass of the sun, where you have convection all throughout the star. So in a star less massive than the sun, you can have convection carrying all of this fuel. So these low mass stars, even though they have less mass, basically all of their mass is available for fusion, which is not the case in stars like the sun, and definitely not the case in the very high mass stars. So this is going to affect the lifetimes of the stars. So the amount of time t that a star spends on the main sequence is its main sequence lifetime. We're about to learn a little mathematical relation, and t is the main sequence lifetime. And that is going to depend on a couple of things. One is the star's mass, capital M. So the more massive the star is, the more fuel it has to burn. And the other is going to be its luminosity. And so the more luminous it is, the faster it's burning its fuel. So here is your formula for the main sequence lifetime. T is equal to 10 to the 10th times m divided by L, where m is the mass of the star, in units of solar masses, so 1 times the mass of the sun, divided by L, which is luminosity in units of solar luminosities. So 1 times the luminosity of the sun. So 10 to the 10th times m divided by L, years. So 10 to the 10th is 10 billion. So what is the main sequence lifetime of the sun? Well, here's how you use this formula. Plug in 1 for m, because the sun has a mass of 1 solar mass, and plug in 1 for L, because the sun has a luminosity of 1 solar luminosity. So now you have 10 to the 10 times 1 over 1, which is just 1, years, which is 10 billion years. So that means the sun will live about 10 billion years, according to this rather approximate formula for main sequence lifetime. So how about if you had a star like Sirius, which has a mass of twice the mass of the sun, so 2 solar masses, and a luminosity of 20 solar luminosities. So this is not exactly holding to the L equals m cubed relation that we had before. So that is another rough kind of rule of thumb, kind of guideline rule. But yeah, if we're looking at Sirius, twice the mass of the sun, but 20 times the luminosity. So how long will Sirius live? Well, you plug it into here. You plug in 2 for m, you plug in 20 for L, and so you have 10 to the 10th times 2 over 20, which is 1/10, and you end up with 10 to the 9th. You end up with 1 billion years. So Sirius, the sun will live 10 billion years. Sirius, twice as massive as the sun, will live for 1 billion years. Now, how about if we have a really high mass star? So this star has a mass of 30 solar masses and a luminosity of 100,000 solar luminosities. So how long is this guy going to live? Way, way less. So plug in 30 for m, plug in 100,000 for L, and then do 10 to the 10th times 30 divided by 100,000, and you end up with 3 million years, which sounds like a long time, but we have to compare it to the other lifetimes of the stars. So in this little table, so mass of the sun 1, luminosity of the sun 1, and that star will live about 10 billion years. 2 solar masses, 20 solar luminosities, well, that star is only going to live for 1 billion years. 30 solar masses, 100,000 solar luminosities, and that one's only going to live 3 million years, which, yeah, that sounds like a long time, but it's nothing compared to the other guys. So I justified this column of the table. This more massive star will live for 3 million years. A star like Sirius will live for 1,000 million years, and a star like the sun will live for 10,000 million years. So, yeah, math-wise, 10,000 and 1,000 are both much bigger numbers than 3. So, yeah, lower mass stars live for a really long time. And if I had one for an even lower mass star, it would live much longer than the sun. So that's, the main sequence lifetime. Now we're going to talk about what goes on in the star once they're giants. So stars are remarkably stable throughout their main sequence lifetime. So over the course that the sun is on the main sequence, so it's been that way for about 4.5 billion years. It'll be that way for about another 4.5 or 5.5 billion years. The sun will have gotten brighter by a factor of 3. So in about 5.5 billion years from now, the sun will be about 3 times brighter than it was 4.5 billion years ago, which sounds like a big difference, but it's way less than a factor of 10. So we're going to say that it's relatively stable. So it's just kind of gradual. The sun is fairly predictable, and most stars are like that. One, they're on the main sequence. So here's the key idea: is after the star runs out of hydrogen to fuse, which that is what makes it a main sequence star, it's going to start going through changes, and those are going to start happening relatively quickly. So, we had a very nice, long, kind of steady run on the main sequence, and now that we get to the next stages, things are going to get weird, and they're going to change real quick. So once the core runs out of available hydrogen, so the sun in its main sequence is fusing hydrogen into helium. Once it runs out of the hydrogen, it's going to lose that outwards pressure in the core. So what's going to happen is all of the gravity is going to start squeezing the core down until it's, tighter and tighter and denser and hotter until eventually the core gets so hot that right outside of the core, we're now at a temperature that's high enough that the star can fuse helium into other things. So your core is getting smaller and it's getting hotter, and right outside that, you've got helium fusion going on in what's called a shell source. So think of that shell around the core. So yeah, again, a couple of contradictory things are happening here. So the core is shrinking and getting hotter, and that heat is driving the outer layers outwards. So core getting smaller, and the outer layers of the star are getting much bigger. So depending on the mass of the star, your star can go from, it can be 5 times as big in radius to it can be several hundred times as big in radius. So as the core is getting bigger and it's getting less dense, it's also starting to cool. So the temperature of the star is going to change because of Wien's law. So the star is going to start to become red as it cools. So thus a main sequence star becomes a red giant once it has used up the hydrogen in its core. So as the star is getting bigger, something a little bit deceptive is going on here. So the star got much bigger, which just kind of with our primitive lizard brains make us think that it must be more massive. It's actually less massive. So the star might have 100 times the radius of the original star. And if you have 100 times the radius, volume-wise, you have 100 cubed as much volume. So you have 1,000,000 times as much volume. But it actually has slightly less mass because it's been burning fuel this whole time. So that means the outer layers are going to have about 1/1,000,000th the density that they did before. So if you can remember back in class, I said the density of the photosphere is only about the density of air here on Earth. So wave your hand through the air, and that's the density of the photosphere of the sun. Much hotter, of course, but that's about the density. And that's the sun right now on its main sequence lifetime. Billions of years from now, when the sun becomes a red giant and it swells up super huge, the outer layers are going to be far less dense than they are now. And once it's that big, even though the star is huge, almost all of the mass is going to be right down here in the core, and you have these way less dense layers all the way out on the outside. So back to the 4 fundamental forces. So remember, we have the strong force, the weak force, the electromagnetic force, and the gravitational force. So the strong force and the electromagnetic force are going to come into play here. So during the main sequence lifetime, a star's core is about 10 million Kelvin, or the sun is up to about 15 million Kelvin. So what does that mean? Remember, temperature is the average kinetic energy of the molecules involved. So if you have 2 helium atoms, should really be helium nuclei. Helium nuclei don't want to be next to each other because they both have positive charges, and positive charges repel, and they're both plus 2 charges. So that's what's going on in this picture here. So at this temperature, at 10 million Kelvin, 2 helium nuclei might be on a crash course to each other, but as they get too close, the electromagnetic force repels them. So they never get close enough to actually fuse. Now, hydrogen, because it only has half as much charge each, you can take two hydrogens and smack them together, and that works. So, yeah, hydrogen atoms do move fast enough to fuse into helium atoms. Because once they start to get close enough, once they get really, really close, the strong nuclear force kicks in and it overcomes the electromagnetic repulsion. And then the weak force turns protons into neutrons, and you do the proton-proton chain thing. So this is helium trying to get together in the core of the sun right now and failing because it's just not nearly hot enough. So that's during the main sequence. Now the main sequence is over, and now the core is starting to shrink and get really, really hot. So eventually the core is going to get up to 100 million Kelvin. So at this temperature, the helium nuclei do have enough kinetic energy that they can smack all the way together. So they're getting closer and closer, and the electromagnetic force is trying to push them apart. But this time they're moving so fast because the temperature is so high that they actually can get all the way together, and then the strong force kicks in and grabs them and holds them together, and it can fuse them into higher things. So in this drawing right here, we have two helium nuclei getting smacked together, forming a beryllium nuclei. So we've gone from having, four helium, so two protons, two neutrons. You go from having two protons each, let's focus on that, being smacked together, and now you have something that has 4 protons and 4 neutrons. So now we have beryllium. And then what's going to happen is another helium will come smack into this beryllium, and you'll end up with carbon, which is atomic element number 6. So this is called the triple alpha process, which is also called helium burning. And it's called the alpha process because we call helium nuclei alpha particles. So basically, at this extremely high temperature, the nuclei have enough energy that if they want to collide, they're moving fast enough that they will be able to collide, despite the fact that the electromagnetic force is trying to keep that from happening. So, yeah, at this high temperature, we have the triple alpha process. So this is how a star in its red giant and yellow giant stages can turn helium nuclei, 3 of them, into one carbon nuclei, one carbon nucleus. So that's the triple alpha process. Now we get to the yellow giants and pulsating stars, also called variable stars. So not all stars have a constant luminosity. Some of them are going to change in luminosity, and we call them variable because their luminosity is varying. So period, we use this a lot in physics and astronomy. Period represents a length of time. In this case, it's how long it takes for the star to go from its brightest to its dimmest and back to its brightest again. So if you're looking at a star like this red giant Mira, so sometimes Mira is very, very bright. And what's going to happen is it's going to go from its brightest, and over about the course of a year, about 332 days, Mira is going to start to get dimmer and dimmer and dimmer until it's only 1/100th as bright as it was. So stars like this, typically they name these classes after the first one that they really study or that they discover or really study well. So stars that are like this are called Mira variables, and they have periods of hundreds of days. And you can see how nice this is. I mean, it's not perfectly regular, but it's fairly regular. You also have some stars that get brighter and dimmer, or more and less luminous, really, but they don't do it in a very nice way at all. So these guys are just irregular. So a T Tauri, irregular variable, is a different one. And these ups and downs are happening on a faster time scale. So, days and weeks, not hundreds of days. So some yellow giants have the property of swelling and shrinking rhythmically, and these ended up being very, very useful. So they're going to change in size, and their luminosity is also going to change. And there's 2 important types of these, RR Lyrae. So this is how you would pronounce it, RR Lyrae stars. And really the more important ones are going to be the Cepheid. Some would say Cepheid, but I say Cepheid stars. So if you're in RR Lyrae, this is a lower mass giant star. And notice how quick its period is. So it goes bright and dim and bright again over the course of just, hours, like half a day for these guys. Cepheid variables, they're going to go from bright. So here we are, bright on day 3 about, and then dim on day 7, and then bright again on day 8. So these guys, their period is, several days. So here's what I just said. RR Lyrae stars, these are the low mass yellow giants, and they have a period of about half a day. Cepheid stars, these are the higher mass yellow giants, and they have periods that are days long, so between about 1 day and about 70 days. And these guys are way more luminous than the sun. The little RR Lyraes, they're about 40 times as luminous as the sun, so yeah, very luminous, very bright. But the Cepheids are much bigger, so they're going to have hundreds of times to tens of thousands of times the luminosity of the sun. The fact that they're brighter is going to make them more useful for what we're going to talk about. So yeah, here is an HR diagram, and main sequence, white dwarfs up here, red giants up here, and you can see where the different types of variable stars fit in. So the Cepheids belong up here on what's called the instability strip. The mirror variables, so these guys are changing over hundreds of days. Yeah, they're up here. This is what the sun ultimately will be, I believe. Will be a mirror variable kind of star. It won't be a Cepheid variable. It'll be a mirror variable. Your kind of sloppy T-Tauri irregulars, these guys with no regular period, these guys are right here. And then your RR Lyraes, so they're on the lower end of the instability strip. They're basically small Cepheid variables is what an RR Lyrae is. So I'll go through this quickly. I feel like this video is starting to get long. How does this variability work? It's because the star's atmosphere and the outer layers are going to behave differently at different temperatures and densities. So we'll start here with this picture. So this star is very small and dense and has a fairly low luminosity. I mean, it's a yellow giant star, so it's still big and not that dense, but it's small and dense compared to other yellow giants. So it has a fairly low luminosity. So it's not actually releasing that much light. So if you look inside here, if you look at these little purple waves, so these are photons being created, and because the star is still relatively dense, a lot of the photons are getting trapped within the star, and only some of them are getting out. So what does that mean? If they're getting trapped within the star, that means the star is absorbing the energy that's created by its own core, and that heats it up, and so that creates this pressure, and the star is going to start to expand. So we went from small and dense and kind of opaque, meaning we're trapping most of the light, to now we're going to start getting bigger because that light that we trapped is giving us energy and heating us up. So now the star has gotten bigger, it's swelled out, so its outer layers are less dense. Well, as they get less dense, they start to become more transparent. So they're now able to let more of the light get away. So now they're letting loose some of that light, which is going to cause them to cool off. And of course, once they cool off, they're losing pressure, and so gravity's going to start to crush them down. And so you go back to this first situation again. And so this is how these stars work. So importantly, it's not like it's turning on and off. It's not like it's switching from one fuel to another. It's always kind of doing the same thing. It's only when it's small and dense, it's trapping most of its own light, which heats it up and causes it to expand. And once it's expanded, well, now it's getting rid of a lot of the energy from its light, which causes it to cool down, so it starts to contract again. And so the cycle repeats. So pulsating stars have this period luminosity relationship, which means the longer the period, so the longer it takes to go from bright to dim to bright, the more luminous the star is. So the person who first really studied these, at least I believe she's the one who first really studied these, is one of those astronomers from back in Harvard with Annie Jump Cannon, and I think she was before Cecilia Payne-Gaposchkin, named Henrietta Swan Leavitt. So she made this very important discovery by studying these variable stars. Why is it useful to know a star's luminosity? Because if you know the star's luminosity, you can plug it into this brightness inverse square law kind of formula and figure out the distance of the star. Remember, there's three variables going on here. Brightness, which you can just measure. Distance, which you want to know, but the stars are too far away to measure directly, and luminosity. And yeah, the nice thing about these pulsating stars is if you can figure out how long it takes them to go through these periods, that tells you the luminosity of the star. So how exactly did Henrietta Swan Leavitt do this? Well, some of these Cepheid variables were actually close enough that she could figure out their distance with parallax. And once she figured out their distance with parallax, she could measure their brightnesses and then figure out those stars' luminosity. And so she came up with this, idea that, well, she kind of discovered that the rate at which the star pulsated told you what its luminosity was. Because if she knew the brightness and the distance, she could figure out the luminosity. Then what you do is you start to look at stars that are too far away to measure them with parallax. So you can always measure how bright they are with your photometer to see how much light you're getting from the star. And you want to know the distance. So you can calculate the distance if you can go back to this period luminosity relationship. So yeah, how does that really work? So say you've got a star, and you don't know, you want to know how luminous it is, and you want to know how far away it is, but you can't figure out how far away it is. So the one thing you can notice is that, oh, well, this star seems to get brighter and dimmer about every 10 days. So you go to this table that Henrietta Swan Leavitt made using nearby Cepheid variables, and you figure out, okay, well, a star that, oscillates this way and has a period of 10 days, that's this guy. So it would have a luminosity of this. So between about 1,000 and 10,000 times the luminosity of the sun. So now you know the luminosity, so now you can figure out the distance. And there's more to the story than this, but this video is getting long, so I'm going to cut it off there. So anyhow, quick review. Low mass stars like the sun, they fuse hydrogen into helium using the proton-proton chain. High mass stars have hotter cores, and so they have an additional way to do this. How do they do it? They do it with the CNO cycle. So carbon, nitrogen, and oxygen. It does the same thing. It turns hydrogen into helium. It's just another pathway for this to work that the higher mass stars, because they're hotter, are able to do. So what is the formula for the main sequence lifetime of a star? That formula is T equals 10 to the 10th times the mass of the star divided by the luminosity of the star, where mass and luminosity are in solar units. And that's how long the star will live in years. So again, the calculation for the sun, this tells you the sun will live about 10 billion years. If you had a high mass star that was both more massive and much more luminous, you plug it in, and that really high mass star is only going to live for about 3 million years. So not a perfect rule, but a good rule of thumb. Just like the mass-luminosity relationship is not perfect, but it points you in the right direction. So does this one. So what is the triple alpha process? This is the process by which stars, once they've ended their main sequence lifetime, can start to burn helium. So main sequence, again, you're fusing hydrogen into helium, and as long as you're doing that, you're in the main sequence. After that ends, the next thing the star does is it starts to fuse helium into other things. So the triple alpha process, you're going to take 3 helium nuclei, aka alpha particles, and you're going to fuse them into a carbon nuclei. So here's the expression for how this works. So what do we call those stars whose luminosity increases and decreases over time? Those stars in general are called variable stars. And there are many different types. There are Mira stars, there are T Tauri stars, there are RR Lyrae stars. The most useful kind really are the Cepheid variables. And these variable stars are so useful because you can figure out the period just with a stopwatch or, a calendar at least. You can measure how many days it takes for the star to vary from bright to dim and bright again. And if you can measure that amount of time, you can work out how luminous the star is. And now that you know how luminous the star is, you can work out its distance. So this is very useful in figuring out the scale of the universe. And it's how Henrietta Swan Leavitt, how she helped solve the whole debate over, are there other galaxies or is the Milky Way only one? And I don't want to go through that whole story because this video is too long already. But yeah, hopefully you're finding this stuff interesting.